Good morning to everybody. Today we are here for the lab number 9 that is dealing with supervised classification, and that will include also a lab number 10 because we are not able to finish all the part related to the supervised classification today. All right, let's start and let's see what we left from the last lab. So you remember that in any case the classification exercise is related also to what we did last lab. So we performed the ISO data classificator, and now we are here in front of these data that are already processed, pre-processed from the radiometric pre-processing. So let's start from here. So you see, this is the situation here with all our data. So we have a bunch of data, but now we remembered what we did. So we are going to the file menu, and we are closing all the files. All right, and we'll reopen only those few files that we need. So you see, no, we don't have anymore any file. We have two views, so you remember, because we created a couple of views in order to perform the operation. But in this time, to right-clicking, we can remove the view because one view is enough for starting this lab. All right, so from where we are starting from the calibrated data, and where we already performed the dark subtraction procedure in order to reduce the selective diffusion components. So you remember we can go to the main menu, and it's, of course, it's not a metadata file, it's an open, simply open file. And let's go to the folder where we have this data. And you see, I have this data that is Amazonas calibrated DAR subtracted, cal underscore ds dot dat. All right. So you remember here we are the color image. You see, this is the 3-2-1 composite. So if we are going by right clicking and we are checking the quick starts of this data, you remember we created a subset of around 4,000 by 4,000 dimension. And let's check what are the characteristics. So you see here is the data. These are reflectance data. All the data are between 0 and 1. You see, you remember we have our 6th reflectance band. If we are going to the histogram, for example, band 4, here you see, this is the histogram of band 4. And you see here we have, we already mentioned that last labs. This is an histogram that is very similar to what I showed you in the labs, in the theoretical part, I'm sorry, when we talked about the digital filtering. So this is a bimodal histogram. So this is a near infrared. This peak here is represented the vegetation, and this one is represented the water. All right. So let's close it. All right. And now we need to start the process with the supervised classification. To do this process, this supervised process, as you know, from the theoretical part, we are starting from the multispectral data set and with the training part. So we need to train the algorithm and we'll then use these training sets by extracting a sample of digital number, in this case, reflectance data, and this sample must be representative and from the statistical point of view, and this sample should be defined by extracting region of interest. Before doing that, let's go to the data manager, to the icon, because in this case, we need to select another display, another display that could help. So, for example, let's open a false color display, so 432 in this case, and let's load this data. And so we have stacked the two different displays. So you see here, you see the water is cyan or dark blue, and all the vegetation is red. So from here, we can start from the training of the algorithm. Here you see we have a linear 2% contrast stretching. You see here. For example, we can go to a Gaussian one. For example, maybe was better than linear 2%. Okay, let's go back. And you see here we have our image in false color. Sorry. At this point, we need to extract some region of interest, some ROI, for the surfaces that we are looking for. What kind of surfaces we have here? In this image, that is, I mean, very didactical from this point of view, because in this image, there's a bunch of water. There is a forest in red. So you have here the deforested area, this brownish area here, and then we have clouds and of course shadow of the clouds. So we have first surfaces. In addition, we have the shadows of the clouds that are not really surfaces, but is something connected of one of these particular feature we have in the image. All right, so in order to start from this here, right-clicking on the name in the layer manager of the image, we are going to the, you see here from the pop-up menu, the new region of interest. All right, so let's click that. You see, when you see here that we have the name of the first region of interest, so we don't have any name. So let's name this region of interest, for example, water. In Italian is acqua, you see here. So water, the name is, is not trivial, because in order, when we are naming this first region of interest, is a fundamental operation which basically concerns the facts of assigning of a priori information that you remember in the ISO data classification, in the supervised classification, this information is assigned a posteriori, after the classification. So right now we are assigning a name and another color. For example, for the water could be the blue here. And remember that this color will be very important after the classification, because whatever what is classified will be classified in blue from the algorithm will be water. So you see, pay attention to the way in which we are drawing this region of interest. So you remember here we have the polygon already set. You see here. I'm sorry again. And so let's try to extract this region of interest. You see here that the car, so here in the water, in the green water, is a sort of crosses. So I can enlarge, because I have to stay away from the radiometric water. So you see here, I'm moving here. So when I re-click on the windows, you see here, I have already the shape of the mouse. You see, when I'm moving the pan, you see the cursor is changing, enabling the pan. And when, I'm sorry, when I'm going to these windows here, clicking on this window, you see now here it's a pan, you see, it's a small hand. When I'm clicking here, you see here, the mouse is rechanged in our pointing cross. So you see, left clicking, I'm staying away with the polygon from the borders. And when I'm going to close this polygon, I'm clicking with the right button of the mouse, and with this pop-up menu, I complete and accept the polygons. And you see that now it's filled, this polygon, with the color I choose for this particular region of interest. So stay away from the borders, And extracting this polygon in a very homogeneous area basically means to maintain the significance of the area. But regarding the representativeness of the area, I need to try to fetch more areas of water, maybe in different conditions. That is, in order to guarantee the effects of being able to extract water in the different condition in which it occurs. For example, I see here that in this intermediate area, I have this water that appears in a different way. So here, you see here, I re-click on that and I extract another polygon. So left clicking and then right clicking and closing that. So using the same ROI, I can draw more polygons in order to ensure the representativeness of the region of interest itself. So pay attention to the mouse. So let's move here. Let's zooming in. All right, again, and reactivate another polygon. I draw another row here. Okay, I complete the polygon, right? All right, so I'm moving out from here. You see, I have already three different region of interest. You see, they appear to be different, while a different condition is here. You see, this water, this downstream channel that is coming back from the northern part of the image, you see, they are different. So, I mean, the water is for sure appears to be different from the reflectance point of view. So I'm zooming in right here. You see they are quite different. So I'm zooming, I'm reactivate the region of interest, and you see I draw an elongated polygon staying away from the borders, and I'm to do the same things in the other channel. You see here, stay very away from the borders, and I'm closing it. All right. So here I have two more polygons in the same rows. So you see, I have 5 different polygons from here, right? You see here, I have 5 different areas, 5 different polygons. So let's add another one. For example, let's go to the southern part of the image in this part here, reactivate and draw a very large polygon here, close that, and I'm also adding this polygon. So very good. So you see, in the region of interest, we have this water, and we have 6 record counts. So it means 6 polygons, and you see here, I can delete, I can pass from one polygon to another. So you see from the second, third, fourth, and you see here fifth, all right, and the 6th polygon, and you see that the image is centered in the polygon. So I have this region of interest. So now I'm going here to in the region of interest windows. I'm going in File, and I can save as the rows. You see here I have aqua, that stands for water, in Italian. All right. Let's save the region of interest .xml. All right. Let's select the folder. All right, everything is okay. All right, let's call that Royce underscore Amazonas dot XML. All right, I forgot to put the underscore. All right, let's edit. All right, and let's open. I have there's something that is not working. Let me check what is it, and no, it is not the underscore, of course. Let's see if I mean it's a problem related to the extension. I'm sorry. Let's call Roy XML. Okay. Let's open it. Okay, it's already existing, but okay, that's okay. Yes. All right. So here we have the Roy XML. All right. So very good. So let's come back to the to our original images. All right. And now, you see, I'm sorry, I use the ROI. So when I want to close it, all right, so I do that by purpose in order to see what is happening. I just see here, clear, right clicking, clear polygon, all right? Okay, so let's use the pan in order to check another image. All right, so now let's have another ROI. So you see here in the icons, in the region of interest ROI tools, we have the water. So let's click on this icon, new ROI, all right? Let's name this ROI, for example, forest, because we are extracting the feature that is connected to the forest. So I'm sorry, I cannot change. All right, here it is, forest. And let's assign this color green, for example. All right. Okay. Let's go to the forest areas. All right. You see here. Let's try to avoid this meandering and rivers that are in the middle of the forest. And so let's go to this part of vegetation. For example, this one. All right. Let's accept this polygon. Okay. Let's zoom out. Let's go to another area. All right. You see here the texture of the image is quite different because we are looking at the crown of the different trees. All right. Let's zoom in here in order to have a certain representativeness of this feature forest. All right. So we have already three different region of interest. Let's go here, for example, where I have a darker area. All right, let's take out this region of interest. Very good. And we have already four different region of interest. Let's go in the middle of these clouds here. All right, let's extract a polygon here. All right, let's close it. And then we can go, for example, in the middle of the water. You see that it's not really a forest, these things here, but let's check what will happen for the here are the different polygons, and we will check what will happen for the vegetation in the middle of the meanders of the Amazon's river. All right, a new region of interest right now. Okay, let's name this new ROI, for example, um, uh, clouds. In Italian, you see here is nuvola. Let's call that clouds. For example, cyan, the color. All right, you see here, and let's go to the clouds and stay away from the borders. Let's extract polygons out of these clouds. This is the first one. All right, let's go to another one. All right, here it is, the second one. Let's close it. Of course, there are not surfaces that we want to classify by their position, but of course we are interested of these features in order to show up as an outlier of the image, because of course these clouds are there in that moment of the acquisition, but of course, I mean, it's not something we want to classify, but they are there. So, I mean, we want to understand if we can extract that. And you see here, we have also clouds just on the river or in the middle of the river. So this one, for example, okay, let's extract that, staying away from the border. All right, so we have four different clouds. Let's check we have something just close to the water. Right here, for example, you see, stay away from the border. We have cyan areas there. Let's stay in the inner whitish area. All right, so Now we have five different record counts for the clouds. So let's go to the new ROI, and this is the last one. All right, let's call the let's for example, I mean, for example here, okay, deforested, deforested, for example. Let's give that another color. This maroon, all right, this one. For example, 153,990, this is the number. All right, let's go to the forested area. For example, these one are the forested areas, you see, that are greenish brownish areas in false color. They are not so homogeneous from the radiometric point of view, but anyway, let's extract the first polygon. Let's go to the other areas. For example, this one, you see, right? So let's draw a polygon in it, all right? Another one here, you see, they are not so homogeneous, so they are contrasted. So let's go in other areas. You see here, you see they are all along a road. You see, this is not very, you see, they are not homogeneous at all in this case, but I mean, they are different from the others. All right, let's go in another point of the image. For example, here in the middle of the clouds, for example, this one that is very greenish, all right? Let's take another polygon and accept that. All right, so in this case, we have, again, five different polygons in this row. And you see, let's resave everything. So you see, we can we have all the different features, all right, that are here also in the layer manager. Let's select all the items, all right? Let's put that in the same file that I call the ROIs, replace that. I can save also the different ROIs in different files, but in this case, I mean, it's making no sense, and consider that also if they are all in the same files, I mean, there's no difference because we can split anyway also the different ROIs, and we save that. All right, so perfect. Now we are ready for example, to compute the statistics from the ROIs, all right? So, for example, if we are going here, the region of interest windows, compute statistics, in this case, this is the deforested area, and you see here, in this case, you see here, I'm just closing these windows in order to check what we have. Here I have a minimum, maximum, mean value and standard deviation for the different 6 different reflectance bands for the deforested region of interest that is composed by 5 different polygons, you see. And this is the spectral signature, or better, the signature belt, where in black we have the mean value, the black lines, in green lines we have the standard deviation, and in red, maximum and minimum value. All right, we can also check the different histograms. You see, these are the histograms for example, the band 4, as they are extracted in the region of interest. So you see, let's go back to the spectral signature. Okay, this is the deforested areas. All right, we can go to another ROI of the other item. All right, so we can go from these things here. As you see here, select the next ROI. So we are in the, for example, in the water, you see here, and compute the statistics for the water. All right, you see here, this is the water, this is the spectral signature of water, you see, and it is completely different from the others. All right, so you see that the mean value is completely opposite in regarding the deforested. Pay attention to the x to the y-axis measurements, because you see for the water we have a very low value. So let's go here from the forest, okay, and complete the statistics. All right, you see here, this is vegetation that is really similar to the theoretical spectral signature. That is the relative maximum, absorption peak in the red, and the peak in the near infrared, and then this decreasing in the mid infrared. And then the other one, the last one, that is the clouds. That is a very particular spectral signature. You see here, we have a very high reflectance. You see here, in particular, here we have something that is really different from the others. So we have our four different spectral signature. So let's close these windows that we extracted with the function, the compute statistics. In these windows, we have a menu here that is here in option, and in particular here you have compute ROI separability. What is this separability? So this is a calculation that when you are clicking, you see here, let's select a ROI for output, for example, forest. Let's click OK. All right, now it's computing the statistics. And you see we have these report windows that is with this algorithm, Jeffrey's Matsushita, that is the transform divergence, that is calculating the separability of the different rows. So concerning the forest, the water and all the other rows are separated from the others. So, for example, you see in this algorithm, ALOSAS, that is a statistical algorithm, understand if two different rows are separable. And if they are, that means that I can use these rows because, and on the opposite, if they are not separable because they are very similar. For example, let's imagine to extract two different species of vegetation, two species of different trees, for example. Maybe, I mean, in this image are not really separable. So in this case, this algorithm, let's mark that as not separable. How we can read this separability? All these values are, let's check, for example, the help in order to better understand what is these things here. Let's go to the index. Let's write down ROI separability. Let's check it if we have something. If we don't have anything, we can check, okay, let's separability is still not there. So may ROI, let's go to the ROI, okay, here, mask. Let's check if we have something that is related to separability. Or wait, let's check the name of the authors of this algorithm. Matsushita, we don't have anything. Let's check if we have. No, I'm sorry. Roy tool. I have some problem with the internet connection in this case. All right. So let's check MV Roy's. All right, in the general one. Okay, interaction, match, programming, separability. You see here. Okay, let's click on that. Okay, let's read. use the Roy separability tools to compute the spectral separability between selected Roy pairs for a given input pair. Both the Jeffrey Matsushita and transformed divergent separability measures are reported. These values ranges from 0 and 2 and indicate how well the selected Roy pairs are statistically separated. Value greater than 1.9 indicate that the Roy pairs have a good separability. All right, so let's check it. You see here they have two, so I mean they are all separable from each other. You see? So this is quite important because if not, I mean you can have issues when classifying because if the rows are not separable, I mean they can mix the results in the algorithm we will use for the classification. All right, so I mean this checking should be done when you are extracting the region of interest. All right, so let's see how we can do that right now. So, okay, ended this first part, we can train the algorithm. All right. So this region of interest is not anyway useful for us. So you see here that we have the region of interest in the layer manager. So let's go to the classification in the toolbox. Okay, let's close the unsupervised classification here. And let's go to the supervised classification. You see here, we have a certain number of classifiers. All right, let's go starting with the minimum distance classification. All right, okay, let's double click on that. And you see here we have, as usual, the windows as the isodata classification. We need to choose the data set. All right. So in this case, you see here, there's also isodata 4. That is not something that we need. So this in memory. Let's use the Amazonas underscore car DS 4000 by 4000 for 6 bands. As in the isodata case, we have the possibility to use the spatial subset. In this case, it's full scene, of course. But in particular, the spectral subset, I mean, you can choose that here. So, like the ISO data, is all in the initial windows of the algorithm. So in this case, we are using all the 6 different spectral bands. But I mean, if we want to check if the classifier, how the classifier is working, like we did in the ISO data, we can choose a lower number of bands. So we are choosing the full scene, all the bands. So you see here, this is the windows that is called minimum distance parameters. All right. So let's understand how it's working and how they are working these parameters. So in this case, you see, we are now choosing the second option that we mentioned in the theoretical part. How many classes we are looking for? So in this case, we are not like in the ISO data that we are changing. We are looking for a certain number of classes, but we have the 4 different classes. For example, I can choose one single class or all the classes. In this case, I select all the items. So in this case, the classifier is looking for these 4 different classes that are the same number of the rows. All right. Here, set maximum standard deviation from mean. All right. So here we have the 2 different choices that were optional in the ISO data. This is the maximum standard deviation from mean that every single cell could have in the scatter plot space, in this case, in the 6th different dimension to the one of the 4 different centroids we have. You remember that the maximum standard deviation from mean is not an absolute value, but is a module of the standard deviation calculated for that particular class. So, I mean, we can check and we can put these particular parameters here. All right. So we can set a single value multiple values of known, for example. If we are not writing anything, this is none. So if we are not selecting in this first case nothing, okay, you see we have a blank value, that means that we are not setting any particular thresholds. So here we are simply saving the data because it's using these four different rows. And so let's choose the name of the classified image. Let's call that mean underscore dist, um, for example, dot data, for example. All right. And now here you have output rule images. Okay. In this case, we have yes. So what are these rule images? That are the discriminating function. I'm not going to explain right now, but let's mark yes, and let's save that with a name. You see, mean underscore dist, for example, underscore rules dot that. All right. So we saved also the rule image, and we will check what the rule images are in the results. So you see, in the first passage, the algorithm reads all the rows values, and now it's classifying. You see here, it's really fast. It's not interactive. So I mean, in just one interaction, of course, is going to the output, and you see now it's zoomed in the middle of the image. All right, and this is the results of the results of the classification is a false color image, you see, and the colors are nothing else of the colors we use for our rows. For example, all the water you see here is in blue because we did choose the blue color for the water row. In maroon, we have the deforested area. In green, we have the forest. And in cyan, we have the clouds. All right? So let's make a comparison of these images with the other. I'm sorry. So let's do another things. Let's go to the data manager, right? In the data manager, let's, in the band selection, we are selecting a false color and we load in a new views, okay? The load data. So we will split the screening into two parts, all right? Maybe it's better to have that vertical, all right? Okay, we need of course, you see that we have the frame cyan. In this case, we are linking the two scenes in order to browse in the same area. So let's go in the principle in the main menu, views. Let's link all the two views, okay? And now you see here we have our linked images. So now when I'm moving in one of the two views, I'm moving accordingly in the other. So you see here, I have some checking on how the classified is performed. So you see that the water is very well extracted in this case, and also this particular water that is different from the Amazonas River is extracted. All the deforested areas you see are extracted, but in that case, you see these humid areas that we have here, you see that this is I mean, you see, it's deforested, and here is a deforested area with some vegetation here, with some parcels, and you see it's completely extracted. But also these humid areas there are marked as deforested areas. So I mean, like that one. So you see that are something that is maybe different. All right, the clouds is in cyan, and the shadow of the image is not a shadow in that case, but it's a water. It seems to be correct. Let's check what is happening in this case. When I'm going to these particular clouds, you see the shadows of the clouds are classified as water. So this is for sure a problem. In this case, the shadows of these clouds are very similar in using this classifier, the minimum distance as water. And you see here, when we have the clouds on the water, it seems to be deforested area. Of course, it's something that is not really okay. What about the forest? You see that the forest seems to be very well extracted from this classifier. You see that I mean? So here the problem that we have is related to the shadows of the clouds. You see here that are something that is marked as outliers of the classification. So at this point, having these results of the classification, pay attention that the results of this image, if we are going to the right button of the mouse in the layer manager, like we did for the ISO data classification, and I'm asking for the quick stats, you see, we will have the quick stats of the classification. So you see here we have the 4 different classes. You see, that is one single band. So we have the mean value and the crosses, the green crosses are the standard deviation and the red crosses are minimum and maximum. And for the 4 different classes, we have how many classes have been assigned to every single class. So the numbers, the digital number are the identifier of the classes. Is the same order of in what we have designed everything, draw in the things, and in the histograms. You see, I mean, this is a degenerated histogram because it's representing the number of cells that is associated to every single class. So, for example, in class 2, you see we have more than 10 millions of different cells. In class 3 we have 300, 2 millions, and more than 2 millions in class 1 and in class 4. So what are these 4 different classes? How we can understand what number is representing a single class. So we are, if we are going to the cursor position value, you see that the data number 2 is related to the class forest. All right. If we are moving here to the deforested, you see that data number 4 is related to the class deforested area. All right. If you are going to the cyan, you see data 3, that is the cloud. If you are going to the blue, that is in this case wrong, is data number 1, that is the class water. All right. So with the cursor position value, you can understand that. What is the rule? What are the rule images? You see, rule images are 5. The first one that is for the 4 different rows, and the first one that is the unclassified. Let's check the first. Let's close. Check out the visibility of these things here. I'm getting out these things here. Okay, and then checking only the water, the rule water. All right. Okay, let's wait just a little bit because I have some problem, because I should have that only in gray tones and not in color. Let me check what's the problem with the rule image. All right, wait a moment. Right, this is the classification. All right, I'm going to the data manager, so it's better. Okay, let's take the rule water and I load in a new Windows. All right, so here it is. So we have a third display. What is the rule image? The rule image is the representation of the discriminant function. So if we are zooming out in order to have all the image, you see This is the whole image. So what is this discriminant function of a minimum distance classifier? This is the distance of every single cell from the center of the centroids of this case. So in this case, for the rule water, all the cells for every single cell of the image, we have the distance in radiometric coordinates of every single cell from the centroid water, okay, in this case of the minimum distance. So we are thinking about the convention in which this image is represented in the display. All the dark values represents a low digital values. That means, therefore, a small distance from the water to the centroids of water. All the bright values representing a higher distance. So in this case, all the darker values are very similar to the centroids water because they are very close, these cells, to the water centroids. So you see here, and that means that in this case, the discriminant function is marking as dark all the areas that are similar to water. All the brighter area, for example, here, the clouds, are very far from the center, so are very different from that. So, for example, if we are going here in the minimum distance rules, and we are going to the quick starts, okay, of this rule image, you see, these are the quick starts. This is not we are not very interested in these the different classes. They are very difficult to read. So in the histograms bands here, we have the four different in the histogram band one, that means that we have the water, the rule image water. So for example, here you see, this is a bimodal function. In this peak here, we have all the cells that are very similar. They are very close distances, so they are very close to the centroids. That means that in that peak there, we have all the area that are very similar to the centroids water, because they are very close to the centroids water, while you see in the other peak here, we have all the cells that are very far from the centroids water. So that means that they are very different from the centroids water. So let's check. If here in this view, 3, this one, I'm going to the layer manager, you see here, and I take the rule image forest. What I'm expecting to see, so I will see all the forests very dark because all the cells that are representing forests are very close to the centroids of the forest in the 6-dimension scatter plots we are using in this classification, while the clouds will be very bright because they are very different. You see? You see, that is very true what I said. And also the water is very bright because they are very different from the forest because they are very far from the centroids. If I'm going to the layer manager again here with the data manager, I'm sorry, and I'm loading the rule image for the clouds, the rule will be darker and all the other things will be very very bright, right? Because they are very different from the centroids clouds. Let's check it. You see that the clouds are very dark. The clouds, you see, the shadows are very bright, and all whatever is very bright is very different. The last rule, deforested, you see all the deforested area is very dark. The water is and the clouds are very bright, and also the forest is brighter than these areas. All right. So you see that using these rule images can be very interesting for a full series of reasons that we see immediately after this classification. All right. So you see here, these rule images are interesting, especially because they are reporting these values that are related to the measurements that we perform, the discriminant function, for this particular algorithm, in this case, that are distances from the centroids in the scatter plot with the same number of dimension of the number of spectral bands we have used. So this is the first rule image, and this is the rule image for the water. So in this case, all the darker cells are representing what is very close to the centroid's water, and whatever is brighter is different from water. You see, the forested areas, forest and clouds are very far away from the centroids in the scatter plot in 6 dimension, from the centroids that is represented by water. That is the mean value of the region of interest we started uh, for the region of interest of water. So in this case, the rule image has the same dimension of the original dataset, 4000 by 4000, because in the rule images, we have a digital number for every single cell of the rule image. You see here in the quick stats, you see, we have all these values. You see that, is ranging from 0 to 1 because we have reflectance. You see here, these are the different rules, the 4 different rules. This is the histogram for water. And you see, we have in this peak all the lower value, the lower distances from the centroids. So in this case, you see here that are very low, so being a reflectance value are ranging between 0 and more or less 1, all right? So in this case, for example, histogram band 1, that is the rule image for the water has a very low values. So very low values, distances from the centroids that you see here is very close to 0. All right. So this is an image like the original one, 4000 by 4000. Inside of this image, we don't have digital values, but we have the distance from this cell in the scatter plots from the centroids, and inherited all this image, all the characteristics of the original image, like the georeferences, but as being an image, for example, by right-clicking, I can use the density slice, for example. So you see, if I'm selecting the rule water, in this case, and I selecting that, you see, I can select the density slice, in which you see here that in violet, I have that peak, and you see, using the rule image, I can extract the water, you see, from 0 to 0.07 more or less. So if I close all the slides and I'm adding a new interval in blue in which I put 0.07, all right, you see here, I can color in blue from the rule image all the water. You see, that is very, very interesting. The possibility not to use the classified image itself, but also the rule image that we use for this classification. All right. You see, in this case, we are using this this area. So you see, for example, here I don't take all the water, but this is only a problem. So, for example, I can put here 0.1, you see here that enlarging this interval, I can extract all the water. You see here, directly from the rule image. You see here, I'm not taking these values there in the downstream channel. For example, I'm enlarging that, 0.2, for example. You see, I'm extracting everything, but I'm also extracting all the clouds, all the shadow of the clouds. So it's too big, 0.15. And you see, I can select that from the rule image, for example. So you see, this is particularly important because that shows us that we can use, of course, the results of the classification, but we can also use the results of the images that are representing the discriminating function, so the measurements that are used for this particular algorithm. So this is very important to consider also the rule image as something that can be used for classifying the different surfaces themselves. All right. So, for example, you can use by yourself, for example, to extract for example, the water from here. You can extract the same for the forest, like in this case, and then just with the band map, for example, to connect all the different extraction you performed of the rule images. And this is very important in our case. So we check whatever we need for the views. So for the rules, I'm sorry, we can remove this view because I mean otherwise we cannot see anything. All right, in order to come back to the screen split into two parts. So we perform this classification. I would simply like to show what is happening when we are redoing the classification, but they're entering different parameters than before. So, for example, the parameters related to the standard deviation. So, re-click twice on the minimum distance. We reclassify the image. Okay, we are reclassifying the original data. So, Amazonas calibrated and in dark subtraction. Here, you see here. All right. Then let's keep that available for the next lab because we will use that with the confusion matrix. So mean this data. Let's reclassify the full scene with 6 bands. All right. Let's select all the items, all the different rows. But now we are checking another things with the only variant before we are checking a thresholds of standard deviation. Let's check, for example, 4 times the standard deviation. I remind you that the values we are inputting here is not an absolute value, but is a module of the standard deviation because we don't know a priori how is big the standard deviation for this particular data. So we are putting a module. That means 4 times the standard deviation. So all the cells that have a distance that is larger than 4 times the standard deviation will not be assigned to this particular centroid. If the distance is less than 4 times the standard deviation, this cell will be assigned to that particular centroid. All right. So if they are not associated to that particular classes, maybe will be part of another class or will not be classified. So that means that in that image, in that classification, we can also have cells not classified because they are not belonging to one of the different symbols. You see here, we can also use multiple values here. So we can change the module, but in this case, for every single class, but I mean, we don't have this possibility. Let's choose the output, the name of the output. For example, min-dist with the same name 1, for example, dot. Let's open that. And let's not extract the rule image. We don't need, because they are the same as before. You see? Because I mean, we are also only putting a threshold. So you see, the region of interest parameters were red, and this is the results. You see here, this is a pseudo color image, of course. You see, in this case, we have many black areas. You see, that is different as before. I'm moving this image. You see that the black areas are not classified areas. You see, these black areas are over a particular module of standard deviation. So, for example, here, in this part here of this water that is very different from the other, is very different from the other, from this water of the Amazonas River. And you see here is not classified, but also these things here, that is the deforested areas, are not very similar to the others. Like, for example, all the clouds are not classified. You see here that the shadows of the clouds are not classified. So, regardless of what we see, you see, for example, here we don't have, for example, in the forested area, the classification. So this is an underestimation problem related to the classification. In this case here, you see, there's a very interesting things. So you remember that the previous problem was the one related to the fact that the shadow of the clouds that are not physical surfaces, of course, because they are of the outliers that of the clouds that are on this image in a randomly position, because the day in which they performed the acquisition there were these clouds, the outliers, the shadows of the clouds are outliers. But you see before that the classification of these shadows are modifying the reflectance of the surfaces where they are projected, these shadows. So that means that changing that reflectance, I mean, for example, the forest in shadow is different from the part of forest that is not covered by shadows of the clouds. So in this case, putting these thresholds, you have not classified areas. So theoretically, it's an underestimation problem, and this underestimation problem, you see that the clouds here is larger than what is classified. But the case that I didn't classify the shadows, in this case, if you are thinking, it's an advantage, because it's preferably if we don't know the surface that you want to consider, not classify, it's better not to classify this area than to classify in a wrong manner. Because if I classify that in a wrong manner, I cannot change the classification label after the classification. Why? If I don't classify things that I am not sure, it's better because I can reclassify later on. So the paradigm when we are performing classification is that very simply, it's better non-classify, to not classify part of the image instead of classify the images in a wrong way. Because if I classify, for example, here, you see here, I don't have, you see on the water, I don't have classified the shadows of the clouds. So in this case, I prefer not to classify rather than classify that areas in a wrong way. Because if I'm classifying these surfaces in a wrong way, I'm not able afterwards to change the classification level. While if I don't classify, so all the black areas, I can think to refine the classification afterwards, after this first classification. So I mean, the general paradigm is that one. It's better not to classify than classify in a wrong manner, like in this way. So you see, I have a hole. So in a posteriori, in this area, I can understand why I don't have this area classified. So you see, this is a very important thing of classification. All right. So in this way, it's better not to classify than classify in a wrong manner. All right. So therefore, we have seen the classification at minimum distance. It seemed to work with different features on the ground. If it's this classification is okay, we will see the next labs when we will check the accuracy of this classification, as I introduced in the theoretical part of the classification, when we will extract the confusion matrix. So at that point, we see that we can pass to the another classifier, for example, the parallelepiped classification. So you see here from the toolbox, we can choose parallelepiped classification. We start again from the original data. So you see Amazonas calibrated and does subtraction. We are using the full scene and all the spectral bands. Let's press OK. This is the parallelepiped parameters windows that is quite similar to the other. So we need to choose the different rows. For example, select all items. You see that in this case, by default, we have set the maximum standard deviation from mean, a single value. For example, in this case, 3 times the maximum standard deviation from mean. Let's change that from 3 to, for example, and so we can compare with the other. Let's put that 4. Every time you are digiting something, you are entering data, press enter in these windows in Envy, because I mean, sometimes there's a bug that is not taken into consideration. As usual, you see, I mean, this menu is very, there are very little items to choose. So let's choose the name of the file. All right. Let's put that parallel piped dot. All right. Let's open that. And let's save also the rule image. All right. So let's save that like parallelepiped underscore rules dot in this case. And let's save that in this way. And let's press OK. You see, this is the classification. This is not again interactive. And so I mean only one interaction in order to finish. So you remember the parallelepiped is very similar to the minimum distance. They are not calculating in this case the distance from a centroid, but the fact that the cell in the scatter plots in 6 dimensions is inside this E hyperparallelepiped in 6 dimensions. All right. So it's very simple the implementation of this algorithm in the software. All right. So in this case, you see here we have the results in the 2 different views. So in this case, the algorithm from the point of view of the operation is very similar to the minimum distance because it continues to work on the scatter plots. And you see, this is the results. And you see that really checking and comparing the 2 results, on the left side, so you have the minimum distance with 4 times the standard deviation, and on the right side, you have the parallelepiped with 4 times the standard deviation. You see, it's quite similar. There are larger areas of shadows not classified, but for example, for the deforested areas, you see, they are larger than before. So that means that are maybe better classified in that case. We don't know. Let's see. You see that the results is definitely different. You see that the forest is more classified than before. And you see that the results, I mean, is you see here, for example, the deforested areas for the parallelepiped, you see, is much better than the other, than the minimum distance, for example. And using these thresholds based on the standard deviation, all right? And you see here that we don't have all these isolated cells because you see here is more or less greenish with not all these black dot pattern. Let's check the rule images. All right, I'm sorry, but we have a bunch of things stacked there. So let's go to the layer manager. You see here we have the water. Load that in a new window, the rule image for water for the parallelepiped. And you see that in this case, the rule should seems to be black. Let's stretch it, all right? You see here, in this case, it's very strange, the rule image of the parallelepiped algorithm. So in this case, seems to be an image in black and white. So in this case, what is happening that if we are going to link the views, all the views, so we are linking everything here, all right? So you see here, and we are going here, for example, in the water, you see all the water seems to be all very bright. How is working the rule image? So let's select this image, all right? This, let's right click here, the quick stats, all right? Let's check it. So you see here that for the rule image, I'm sorry, here it was enlarged, all the windows, they are representing data are ranging in the rule image from 0 to 6 and that are very strange. You see here, for example. So what does it mean? The rule image, for example, let's see the histogram, the band 1, that is the water. You see that the major part of these points are represented in the point 1. The rule images is with higher values, the values 5 and 6, more or less, uh, that are closer to the parallelepiped, are representing the belonging of that cells to that particular class. All right. So in this case, when we are clicking on the right button, we can perform the raster color slice. For example, selecting the rule image water for the parallelepiped. Okay. You see, we have only 6 classes, but you see that that's class number 6. You see the red one, or better the 7 in this case, because we have also the class 0, seems to be the water. You see here, I'm sorry again, it's enlarging. So you see, this class 6 seems to be the water. So you see here, whatever is in class 6 is what is belonging to the water. In this case, you see, if it's not 6, it's 5 or 4. So I mean, higher degrees, higher number are representing the belongings of this particular class. For example, 5, 6, class 5 and 6 should be represent all the water, for example, here. You see? So you see that also here in this parallelepiped algorithm, the rule image can be used for post-classification. All right, let's close also these views after the density slice. You can do the same thing by your own using the other rule images for the parallelepiped. Let's right click on that and remove this view. All right, so I have again and back the two classification we had before. In this case, I mean, I need to move that, all right, okay, I need to pan. And these are the last two classifications. The last example I want to perform in this case is just, I mean, in the left side, you have the minimum distance. On the right side, you have the parallelepiped, you see here, by clicking cyan frame, but you see that I have also highlighted the name of the file. You see that from the just viewing, it seems to better works the parallelepiped. Let's check how we can use the parallelepiped classifier without any threshold. Let's check how is working the parallelepiped without any thresholds. So that means that all the cells will be assigned to a particular class. So because you remember that if we put a threshold on the standard deviation, we will have the unclassified data. If we are not putting any thresholds, and let's do that with the parallelepiped, let's click twice on the parallelepiped. Let's use the original image, Amazon car dot subtraction dot dat, the full scene and all the 6 bands. All right. And you see that, I mean, of course, if we are using a fewer number of bands, the results will be different from that one. And if you want to check that, let's do that by yourself, maybe using these two classifiers with a lower number of bands, for example, only the visible, in order to check what is happening. Let's use all the different classes, but not put any thresholds. So single value before 3 times, none. So we are not using any threshold. Let's save the file. Let's I'm sorry, not this one, parallelepiped 1, for example. All right, let's open that. Let's not generate the rule image here, and let's press OK. All right. Now you see it's classifying. All right. We will have that stacked over the other. Here it is. You see that if we are not using thresholds, this is whatever is in the rectangle without any thresholds. So I hope you see here there's a bigger part of the image that is not classified. So what is happening if you are not set any thresholds? That imagine that we are using only 2 bands as like in the theoretical part. All these things, we are using a rectangle in the considering only 2 bands without any standard deviation. All right. So these rectangles are relatively small in comparison with the others. So in this case, the rectangle was small, and so there will be a bunch of cells that are not classified. So let's get out in visualization these things here. Putting a larger standard deviation, I'm enlarging the dimension of this parallelepiped or hyperrectangle, and so I will classify more things. All right. So if I don't set any standard deviation thresholds, this is using the real value, so that means 1 times the standard deviation, and so the results will be an underestimation of the classification. So there will be very few cells that will be encompassed in this particular rectangle. So you understand these things here. So if I want to have, in this case, you see here, without any thresholds, the rectangle will be smaller, and so very few cells will be classified in that particular rectangles. All right. So this is the results of these things. If I want to increment the number of cells that are in every single class, how can I do that? If I want to fill these particular holes in some way, how can I operate these things here? So let's check. Let's reclassify the original data, full scenes, 6 bands. Let's press OK, select all items. And now I put instead of 4, let's put 6, for example, and enlarge the rectangles. All right? No rule images. Let's save that in another file, parallelepiped number 2, for example. Let's open that. Okay. Let's press OK in this case. All right. The results will be stacked, overlaid in the right part here. And the results maybe will be that larger areas will be classified. You see here? That is happened what I was thinking about. Most of this part will be filled by classification, you see? Because I mean, we are using larger rectangles in this way, all right? Very good. So 4 times and 6 times. You see here, 6 times. I'm not now in this case evaluating the accuracy, but I mean the results is that that all this part is classified. You see, I'm sorry. Here, this part of deforested areas is better classified with 4 times. If I'm using the 6 times, let's click here. You see that is seems to be filled, and you see that all the shadows of the clouds are not classified. That is correct. You see, because I mean it's an outlier of the image. You see that in this case, it's better not to classify. All right, and all the water also here are not classified. That is very good in this case. You see that I mean the result seems to be correct. All right, so with today we have finished the first part of this supervised exercises related to the lab number 9. Next time we will have the lab number 10. That is the second part of the supervised classification, where we'll use other classification algorithms, and we will also use the confusion matrix in order to check the accuracy of the different classification results. All right, so we will use this confusion matrix not only with the last two algorithms, but also for this minimum distance and parallelepiped. And so keep the results ready for the next lab. Okay, so very good. We will do all these different operations. So for today, it's enough. Thank you for your attention, and we will meet again for the next lab. Take care and never give up. Bye-bye.